Anyway, so good morning, everyone. Last time we introduced matrices and we talked about how we can use them in graphics, for example, to solve linear equation systems. But I also already mentioned that we will be using them a lot to do transformations of vectors, and this is what we're going to do today, the transformation of vectors by using matrices or matrix multiplication in particular. I already showed you that quickly last time. The idea is if we take a vector and interpret it as an n cross 1 matrix, so a column vector, and multiply it, then we can multiply it with an n cross n matrix, and the result is again a vector of the very same dimension. And of course we can use that to manipulate vectors to create new vectors from existing one and to transform the vector into another one. And let's just look at, so we will start today with 2D cases, and then later in the end we'll also cover 3D, because the 3D is very often just a very simple generalization of the 2D case, and the 2D case is of course easier to understand and also easier to draw. So maybe the most simple transformation is of course just a simple scaling. So you see here a matrix 2 0 2 0 2 0 0 2, and if we multiply that with a two-dimensional vector, we get again a two-dimensional vector, but now each coordinate of the vector is scaled by a factor of 2, which in the end result of course also scales the whole vector by a factor of 2. So you see here with this very simple matrix multiplication we can manipulate the vector, we can do a scaling by a factor of 2, but also by all kinds of other factors of course. Now of course if you look at the vector you can say, well, this is pretty much the same as we get with scalar multiplication of vectors. Why do I need matrix multiplication? And of course you're right, but the point is of course that for matrix multiplication we don't need to restrict ourselves to this so-called uniform scaling where we scale each coordinate with the same factor, but we can also do a non-uniform scaling where we give each factor a different scaling, each coordinate a different scaling factor. So for example we can reduce the x dimension by half and increase the size of the y dimension by 3, and then we get a different object here that is non-uniformly scaled. And that is of course something you cannot do with simple scalar multiplication for vectors. So in general we say if we have a matrix that has a diagonal matrix, remember diagonal matrix is a matrix where only the values in the diagonal are unequal to 0. So if we have a diagonal matrix, then of course multiplying it with a vector gives you as a result a vector where just the coefficients of the vectors are scaled by these values, these coefficients in the diagonal. And of course we can use that to increase, decrease or the size or move a vector, change the orientation of the vector if we choose the AI's as negative values. So you see it on the right side, this image for that illustrates it a little bit. But that is again for uniform scaling, which of course is pretty much the same image as we had for scalar multiplication. But if you have then non-uniform scaling, you can also change of course the direction, which is certainly something that you cannot do with scalar multiplication. Good. Now there are of course a lot of other examples. So for example, what happens if we take one of those AI's and set it to 0? So for example, if we set the x coordinate also to 0 and just have a 1 for the y for the A22 in this case, which corresponds then to the y coordinate, then of course we get a vector where the x value is always 0 and the y value just keeps its coordinate, and that is geometrically, you can see this as an orthographic projection towards the y-axis. So this is actually should have written this down here, this is the y-axis, this is the x-axis. And then this is of course just a projection onto the y-axis because the y value stays the same and all the x values are set to 0. And it says here orthographic projection. We'll talk about projections later in the first lecture, I think, after the midterm exam. But an orthographic projection is basically a projection where we project everything at the right angle towards the projection area. So in here you see the projection area is the y-axis and everything is projected here with a right angle, and that's why we called it an orthographic projection. And you see we can do this very easily here with matrix multiplication. Now So far we've looked only into having values in the diagonal, but of course we do not have to set these other values to 0. We can also give them values larger than 0. And for example, what happens if we choose these values here to be 1 and choose the diagonal to be 0 is that we implement a reflection. You can see it here. What happens if you think about what happens if you take an object and reflect it on the line y equals x, so this 45-degree line here that splits the 2D space, then you see it from the image. You can see it that what happens, it just swaps the x and the y coordinate. It's just exchange the x and the y coordinate with each other. And if we want to implement that with a matrix multiplication, well, then we just set this first value here to 0, and here the second value to 0, and this here to 1. And then, of course, we have swapped the y and the x value here. So you see here, by this matrix multiplication, we can achieve this reflection on the line y equals x. You can do, of course, a lot of reflections on other lines. So, for example, at the y-axis, at the x-axis, at any random line, of course, but the y-axis and x-axis and this axis is, of course, are the simple cases. And you will have a lot of examples of this in the tutorials. Good. So, so far we just looked into situations where we only had in this general equation here where always one of these was always 0, so the result only depended on one of the two coefficients from the vectors that we had here. But of course we can fill in all kinds of values here. So for example, we could also have ones in the diagonal and a 1 here. And geometrical and from the arithmetic you see that the result of this is that the y value stays the same because we have the 0 here, of course. But the x value gets the y value added to it. And if you look at this in what this means from a geometric interpretation, it's something that I already mentioned shortly last time in relation to this proof where we had this parallelogram, and I said if we shift it a little bit, the volume doesn't change, and I used the phrase shearing already. So shearing in graphics or in geometry is interpreted as pushing everything sideways in a certain direction, like informally described. You see it here from the image. We say we are shearing in x direction. So this is the x direction. This is the x-axis again. So we take every point here and we shear it in this direction. Also the same here and here. And the amount of which we are shearing it depends on the y value, which means the higher up it is, the more we're pushing it. So you see we're taking the y value here and push it. We're taking this x value here and push it as far as we are high up here. That was a weird sentence. So you get the idea. You depending on how high you are, the further you push away. But the important thing is, of course, the y value here doesn't change. So what we're doing here, we're pushing everything to the side in one level. So everything that is on this level here, on this line, stays on this line. It just moves in x direction because this is the direction in which we are shearing, which is illustrated here by adding this value here to the x coordinate. Of course, we can also do this in the y direction. Then, of course, in our matrix, we have a 1 here and a 0 here because if we're pushing in the y direction or if we do a shearing in the y direction, we want to keep everything at this level, at the x level. We want to keep everything, but we want to push it only in the y direction. So we're adding the x value to the y value here. And again, the further away you are, in this case then to the right and not up, the more you're pushing it in that direction. So this here gets pushed further than this one, and this one doesn't get pushed at all because here we are at 0. So 0 plus y is, of course, y again. Good. And of course, we don't have to just push it with a fixed value, that the y value, just adding this actual value, but we can also scale this value, and that is then of course the general case for shearing, where instead of a 1 we have an s here. So we multiply this value with s, some sort of scaling, and then add it to x, and that way we can also do, for example, something like this So we shear it even further. Just, yeah. Sorry, I just needed to check something because it reacted a little weird here, so I wanted to make sure the recording is okay. Good. All right, so we see we can use matrix multiplication to create all kinds of different transformations with vectors by choosing these aij values in the matrices appropriately. And of course, some of them are quite strange, don't make any sense, but a lot of them, if we choose them appropriately, make a lot of sense in geometry, and we can achieve certain operations with it, so we can make certain transformations. The question is, of course, what kind of transformations can we do? Can we do all kind of transformations? And it turns out, of course, we cannot do everything, but we can do a very good and very large and very useful subset of it, which are the so-called linear transformations. And linear transformations, we had this before, the term linear. Remember when we use the linear equation system, every time we're using linear, it means that the variables that we have are only to the power of 1. And this is the kind of transformation that we can do here, and we can define such a linear transformation by two characteristics, and we say if a transformation fulfills these two characteristics, then it is a linear transformation. And the first characteristic is that if we have a vector like u plus v, like we have it here, and we apply this transformation to it, so we say we apply this transformation t of u plus v to the vector, then we get the same result as if we apply the transformation to the individual vectors, and then add up these two to the transformation here. So these two here are the same. Or if these two are the same, then one of the conditions for a linear transformation is fulfilled. And the second condition is, I don't have an image for that, but the second condition is if we have a vector v and a scalar multiple of that vector, then it doesn't matter if we apply the transformation to the vector v and then do the scalar multiplication, or if we do the transformation to the already to the vector that where we already did the scalar transformation. And if these two conditions are fulfilled, then we say we have a linear transformation, and these are exactly the kind of transformations that we can do with matrices. And we see that we can do them with matrices very easily. If you remember what some of the characteristics that we discussed last week, and one of them was that matrix multiplication is distributive over addition, which means if we have the sum of two matrices and then multiply it with another matrix, it's the same as if we do it individually and then do the sum of it, which is exactly our first condition. And the second condition immediately follows from this how multiplication with a scalar is defined for matrices. If we multiply a matrix with a scalar, we get the same that is basically the same as the definition of multiplication with a scalar. So if this T is represented with a matrix, then we see that this condition is obviously fulfilled because of the way how multiplication with a scalar is defined. Good. There is also the option, of course, to take these two conditions here and summarize them. So sometimes when you look at the literature or when you have to do an exercise or an exam question, it is also used this equation here, which is clearly that this is basically, if this is fulfilled, then these two conditions are fulfilled, or the other way around. If these two conditions are fulfilled, then also this one condition is fulfilled. So they can be used interchangeably. It's just a way of, sometimes it makes the writing easier, or if you want to have a proof, like in earlier exams, we had an exam question show that scalar multiplication, that scaling is a linear transformation, and then what you had to do is basically prove these two conditions for a general case of scaling with a scaling matrix, and instead of proving these two conditions, you could have just proven this one, which reduces the writing a little bit, and then of course that makes it easier, but other than that it is exactly the same. Good. So we see now, we know now what kind of transformations we can get, and we can get, we saw already some very simple examples where we could just by looking at the matrix could already identify what kind of transformation we have, or the other way around, if we said, okay, we want to have a scaling, how should the matrix look like? It was very easy to come up with how I have to write those aij's down to get exactly this effect that I want. Now, this is a more complicated example where, or complicated, it's a more like, I'd say, less obvious example. If we want to do a rotation around the origin at, for example, an angle of 45 degrees in a counterclockwise order, then this matrix here is the transformation matrix for it. Or in general, we can also have the general case if we say just any angle in counterclockwise order, so in this direction here, then this is the transformation matrix for it. If you want to rotate in clockwise order, we have this transformation matrix, and that should be obvious, of course, because in rotating in that direction is basically the same as rotating in counterclockwise direction, but just with the negative angle. And if you remember how cosine and sine are defined, these functions, then you see that this is just the negative version of it. So if you put the negative angle here into that, so if you just take minus phi here, you will end up with exactly this matrix here. So that is obvious, but the question is, how do we get this matrix here? Because that is something for the scaling and the reflection. I said, yeah, you just look at the formula and then you immediately see the result. It's obvious why this is the correct matrix for it, but here, at least to me, when I look at this at first, it was not really that obvious. So how can we come up with this? So in general, how can we find the aij matrix values for a transformation matrix that is does a linear transformation, but it's not really that obvious to see? Let's look at the simple examples that we had. So maybe we can identify some pattern here that helps us in this. And what we do, sometimes it helps to use these simple examples, just with very simple cases or with very special cases. So let's just see what happens if we apply this to the base vectors, the vector 1, 0 and 0, 1 from our Cartesian coordinate system. For the scaling, of course, if we multiply the scaling matrix with A and with the vectors 1, 0, 1, 0, we get, of course, A, 0. So that is this B1. If we multiply it with 0, 1, we get 0B. For the shearing, if we apply this, then of course the y value doesn't change. So in the first case it stays 0, in the second case it stays 1. In the first case, 1, 0, the y is 0, so that also doesn't change. So that is 0 here. So the x value, we only have the x value here, so the b doesn't change, it stays the same, but the b1. But the b2 changes, of course, because here we have 1, where is it here? 1, 0. And that means, of course, we have here x is 0, but we add a 1 to it, and that means a 1 times s to it, and that means we have s1 here. For the reflection, we said already that basically just swaps the x and the y coordinates, so obviously these are the two solutions to it. And for the rotation, we see that, yeah, if we have 1 and 0, then of course in the first case we only end up with the cosine and the sine as the values, and in the second it's minus sine and cosine. Now, I said we're doing this, maybe we can identify some pattern with it. If you look carefully, then you will see obviously the pattern. The pattern is that these vectors here are exactly the column vectors of our matrices. So if we apply our transformation matrix to the base vectors of the Cartesian coordinate system, we get exactly the column vectors of the matrix. But the other way around, that also means if we don't know the matrix, we just have to think about where will those base vectors end up when we do this transformation. And this vector where they will end up is then exactly the column vector of our matrix. So, and this is of course clear when we look at the equation, how we calculate it. It is clear that if this is 1, 0, then of course this is multiplied with 1 and this is multiplied with 0, and then we add up. So we will always get the first column of the matrix here. And the same for 0, 1. Then we have 0 here plus 1 times this here. So we'll always get the second column for 0, 1. So that is clear if we apply to the base vector. The question is, or what it's not, maybe not that obvious, is why does that also transform all other vectors in exactly the way that we want to? But here it comes into play that we have a linear transformation with this characteristic here, which nowadays also it makes it convenient to write it in one line, because we also learned that we can represent each vector in a Cartesian coordinate system by a linear combination of the base vectors. So if we have a vector xy, we can represent it as x times the first base vector time plus y times the second base vector, and that is of course then xy. But this is, if we take this vector here and apply now the linear transformation to it, then of course, it's already written here, then of course we have this here, and because of that, let's call it 1 here, we see that we can do exactly that, and that way we see that this transformation matrix must, or the column vector of this transformation matrix, the first one must indeed be the image of the first base vector, and the second column must be the image of the second base vector. And that way we see that it also works for any kind of vector in our coordinate space, that if we apply this matrix to it, it does exactly this kind of transformation that we want if we have chosen the column vectors in a way that they map the images of the base vector to the images of the base vectors after we apply the transformation to it. And that of course makes it now very easy to come up with this matrix here. And I just have the case for the first column here, or the first, means we have to look at the first base vector. The second one works in the same way, so you can do it as an exercise. So we have the first base vector, 1, 0, and then we say we want to rotate about an angle phi counterclockwise. That means we have an angle, a target that is something like that at an angle phi. Now if you look at this angle here, you get again a triangle with a right angle. And that means we can apply, we can describe the sides of the triangle with the cosine and the sine of phi. And that means, of course, the x is the cosine of phi, the y is the sine of phi, and this is exactly the first column here. So this first column is exactly the image, so the cosine and the sine is exactly the image of the base vector when we apply the transformation to it, and that makes then our first column. So you see, this is a very simple way and very easy way to come up with this matrices that are not as obvious as the cases we had at the beginning. Good. Now, one of the problems with this, so now we can apply this transformation to all kind of vectors. So if we have a complex object or a more complex object, like for example this rectangle here, we can apply it to all vertices, and then we can make a transformation of that object. And that works very well, and it works in all cases, but there is of course one issue. We have to be careful if we have an object and we use normal vectors, for example for light calculation. Then of course when we do the transformation, we also want to use that normal vector for the light calculation. Now if we the easiest way would of course be if we already have calculated the normal vector, that we then just apply the transformation to it, and then we can also use the normal vector for the transformed object. But the problem is that the normal vectors do not transform correctly with this transformation matrix, and you see an example here on the right side where we have the shearing. And you remember normal vectors, of course, for a flat surface, it's clear it's just a vector in a right angle to it. But in general, for all kind of surfaces, we said that the normal vector is the tangent rectangular to the tangent of at this point. So this is why the general notion here speaks of a tangent vector. And you see here, if you apply the shearing to the tangent vector gets transformed correctly, but the normal vector also shifts because it points up in that direction, whereas the tangent vector is at this level where the shearing doesn't change anything. Whereas here, of course, it is that the normal vector is at the level where it doesn't change anything, but the tangent vector shifts and the surface shifts. So that means also, the normal vector should shift here, whereas here actually it should stay the same. So you see here it doesn't really work that well. So one solution could be, of course, recalculating the normal vectors for each transformed object, but it would be much easier if we could just apply a transformation matrix to it. And the good thing is there is one transformation matrix, and it is quite related to the original one. It's just the inverse of the original one and then the transpose of it. And if we apply that to the normal vector, so here for the object we apply the transformation matrix A, but for the normal vectors we have to apply the matrix A, the inverse of A transposed, and then we get the correct normal vector and not this wrong one. That would be the one that we get when we apply the matrix A. And this is the one we get with this matrix. And if you don't believe me, then we have a little proof for it. So how can we see that? How can we verify that this is indeed a correct matrix? First of all, we know that the tangent vectors are transformed correctly. So if we take the tangent vectors here, the blue ones, and apply the matrix A to it, we know it's transformed correctly. You see in the top it doesn't change. Here it changes in the same way as the surface changes. Of course they are transformed correctly because they are related to the surface, which is the one that we transform. But we also see that this vector n, when we transform it, is not transformed correctly. So the goal that we have is we need a matrix NA, which hopefully will then be this one here, that transforms n correctly. So n multiplied with this matrix NA equals then the normal vector. I called it n because that's the real normal vector, whereas the wrong one I called then NA because that's the wrong one. That's the one that created with this matrix A. So now we know that the original normal vector n is perpendicular to the tangent vector. So here, these two vectors here, oops, what's going on here? Here, n and t, these are perpendicular to each other, which means that the scalar product, if we write it in this matrix form, n transpose times t must be 0. And now we do some arithmetic tricks, basically. We say if we multiply something with an identity matrix, it doesn't change the result. So we can just put the identity matrix in the middle here. But if you remember how the inverse was defined, and you know that the inverse times a matrix times the original matrix is exactly the identity matrix. So we can write it also like this here. Doesn't change the result, it's exactly the same. But if we do that, we see here we have on the right side a vector, and that is exactly the transformed vector. But we also have a vector here, and since the scalar product of these two vectors is 0, these two vectors must be perpendicular to each other. Now if that vector is perpendicular to this blue vector here that is transformed, then of course it must be a normal vector. So here we are. So this vector here, yeah, it's annoying when it doesn't fit on one page, but if I make the font smaller, then you can have a hard time reading it. So this vector here must be our normal vector. But because we have done this in matrix notation, we had to use the transposed vector. So the real normal vector that we want to have as a column vector, so this is the transposed vector, of course. The real vector is the transposed of this one, but that means Now you remember this one sentence or a characteristic that I proved last time. If we have two matrices, make it transpose, we can also write it like that or calculate it like that. And that comes in quite handy now, because now we can write it that way, that we have the vector n and then the transpose, and then we end up with the vector here, and we have exactly this matrix here that we were looking for, or that I claimed before, that this does the right transformation. And now you also have the proof that this does the right transformation. Good. All right, so so we have to be careful when we do transformations with normal vectors, but otherwise we can do transformations of objects very easily, and we'll do this very often in a lot of situations to create new objects, and also for other reasons that we will see later. And sometimes when we do all these transformations, it is important, you will see an example later, that we are able to do the same, do basically the reverse transformation. So we do a transformation, and then we want to do the same transformation back. So we want to transform everything back to its original position or style. And these transformations are called inverse transformation. And if you look at it, for example, for scaling, actually when you looked at the image, you probably saw that, or you might not have realized it, but I purposely did not include like notations indicating in which direction we make the scaling here, because it is actually, if you look just at the image without what I've just drawn, you cannot say which one's the original one, because you can do in both directions, and both directions are just a simple scaling. So the inverse operation of scaling is again a scaling. It just scales with other factors back to the original ones. And if you look at the example, then you can see, of course, that if you change the y-coordinate by half, then the reverse option is, of course, just double it again. So instead of 1/2 here, we have 2 here, and the same here. Instead of increasing it by the size of 3, when we go back, we shrink it by 1/3, so we have 1/3 here instead of 3. So that is easy to see from the image, but also if we look at the matrix, and if you are a little familiar with matrix multiplication, you will realize that this is actually exactly the inverse matrix. So this here is T times the inverse is I, the identity matrix. And this is not a coincidence, but this is actually always the case, that when we take a transformation, and then we take the transformation matrix and calculate the inverse of it, and then apply it again to the object, we get exactly the reversed operation. We end up exactly with the original object again, because it is just the one-to-one counterpart of the original transformation, or exactly the opposite of the original transformation. So we can see, and of course, in this case we easily see it, but of course if we do not easily see it, then we have ways to calculate it. For example, we can calculate the inverse matrix by using Gaussian elimination. I shortly mentioned it last time, but you have an exercise in a tutorial that explains it, and that also asks you to do the calculation, which is then also, if you have done it once, then you will easily understand it. Good. So we know how to do it, and we can also, of course, look at all the examples of all the cases that we had so far. So, for example, for the shearing, from a geometric, actually that image doesn't make sense here. That's only for the y direction, for the x direction. Forgot to delete it. Sorry. If you think about it from a geometric point of view, of course, if you push something to the side within one level, then the opposite operation to it would, of course, be just push it backwards, and push it backwards but the same amount, but again, stay in that level. And that means, of course, if that is just plus s, or sy, then the opposite direction is, of course, we push it by the same amount, which means minus sy. And that means for the transformation matrix, we get a minus here. And again, if you don't see it from the image immediately, then you can also get this inverse transformation matrix by just calculating the inverse of this matrix here. So this is just the inverse matrix. Good. Good. For the reflection, again, if we look at the image, we see that a reflection and a line at the line x equals y, which just swaps the coordinates, is, well, pretty much the same. It's just, again, a reflection. We just reflect the object a second time, and then we end up with the same object that we had originally. So the transformation matrix is, the inverse operation is exactly the same as the original matrix. And if you take the original matrix and calculate the inverse, then you will also see that it is indeed the same. You end up with the very same matrix. Now for the orthographic projection, it's not that obvious from the image, and also if you calculate the inverse matrix, you will realize it's not that obvious. It's not only not obvious, but it's also not possible, because that is undefined. And you see that from the arithmetic, because if you do Gaussian elimination, you will end up with exactly this one case that we had, where Gaussian elimination doesn't give you a solution, where you have a line only zeros equals a value unequal to 0, in that case 1, and that is not solvable. So you cannot calculate the inverse, and we also said the inverse doesn't always exist, and this is an example for it. Also from a geometry, it is clear that you cannot uniquely specify an inverse operation. With all the examples here that we had before, just by knowing the result object and the transformation, without any knowledge about the original object, we can recreate it. But here, if we don't know the original object, if we just know the result and the transformation, we don't know what the original object was, because it could have been also this one. So also from a geometric point of view, it is not clear what would be the result of the inverse operation if we don't know the original object. So that means that we cannot define the inverse operation to this. Good. Now, we've already seen, I already said, if we do a transformation and then we want to go back to the original object, we can just do another transformation, which is the inverse case. But of course, instead of the inverse, we can also do any kind of other transformation, because once we have done the first operation, we have a transformed object, which is just a regular object in our space. Then we can apply another transformation and another one and another one. And the interesting thing now is when we do this with matrix multiplication, of course, we can combine those matrices into one, or we can combine those transformations into one single transformation that is represented then by one single matrix. And that is because matrix multiplication is associative. So if we have a vector and apply a transformation matrix to it, and then another transformation matrix to it, we could also take these two transformation matrices, multiply them with each other to create one transformation matrix that, instead of doing this and then that, we directly do this in one step by using this matrix here. And so that works because matrix multiplication is associative, but also keep in mind matrix multiplication is not commutative, so you have to be careful in which order you apply it. And you see it with an example here. The first one is this one that we had in the previous slide also, that will end up in this object here. And the second one is just applying the same two matrices, but are the same transformations in different order. And from the arithmetic, we know already that this is not commutative, so we already saw that it doesn't work out. And this example again proves it, that it doesn't work out. Also from the geometry, if you think about it, I didn't draw it here because it would have to go beyond the screen. So if you do first the scaling, you end up somewhere here, and then you do the reflection, you end up somewhere here. So you see you end up in a completely different object here. This is AB and this is BA. So you see also from the geometry, it's wrong to apply them. You get a different result if you apply them in a different order. So you always have to be careful with the order. Good. So as a little summary, you see that we have different ways of finding transformation matrices. The first one was what I just called here informally educated guesses, where we just basically looked at the formula, and an example is the scaling. Of course, if you we want to scale, then it's clear that we just say, just put these two to 0 and then just put the scaling factor for each coefficient here, and then you have your scaling matrix, which is so simple that you can just by looking at the formula you will come up with this most likely. If it is more complex, we can use the fact that these column vectors are the images of our base vectors. So we just have to, if we want to make a transformation, just have to think about where will those end up when we do the transformation. And if we have those vectors here, those are exactly then the column vectors here. Or, and now we have a third way with this composing of matrices, we can also do more we can create the matrices just the other way around, as I said it here. Here I said we take we apply multiple transformation matrices to an object, and then we combine it in one matrix. So we just have to do one matrix multiplication. And then we have a more complex transformation which represented with just one matrix. We can also do it the other way around. If we want to make, or look at it the other way around, if you want to make a very complex transformation, you can think about what kind of simple transformations would I have to make that more complex transformation. And then you say, okay, I know the transformation matrices of all these simple transformations, so I can just calculate this one more complex transformation matrix by doing the matrix multiplication of the simple matrices. And that would then be a third way to come up with transformation matrices. And this is an example here. We already talked about a rotation around the origin. So if we want to rotate an object around the origin, we already know the transformation matrix for it. That was actually the example we used for the second case here, where we looked at the image of the base vectors. Now, if we want to rotate around a random point, we don't know how to rotate it there. We could look, of course, again for the base vectors, but that is also not that easy and not obvious in this case. What might be easier in that case is to say, well, let's just split it in smaller, simpler operations that end up in the very same transformation in the end. So we could, for example, say we take the origin, we take the rotation center, move it to the origin, and move everything else with it. Then we do a rotation around the origin, which is something we already know how to do with this matrix, and then we just move everything back. And then, of course, these are then the same operations that we had, we end up in the same result as if we had done the transformation here. So we split this more complex operation in rather simple steps that we can easily control, where we know the result of the transfer, we know the transformation matrices, and then we are done. The only problem here is we don't know yet how to do a translation. And the big problem is, of course, we cannot do a translation with linear transformation. Because if you look at what you get with a linear transformation, you will always get something that depends on the variable values here. The only way it doesn't, for example, this first one doesn't depend on the y value is if we set this to 0, but then we just have a scalar multiple of x, so we do not have something where we add something. So for a translation, we always need to add a constant value to x and y. So if this is our vector and we want to translate it here, we need to add a constant value to it, a constant factor to it, and that is something you cannot achieve with this kind of multiplication. It's not possible. If you don't see that, some people always have problems with this when they're not that familiar with it. Just try it with some examples. Try to think about a case where you say, okay, I just want to translate them, for example, by 2, and then try to write it down, and you will see you will not succeed because you always have this variable factor, so you will not be able to add a constant factor with this. So we cannot do it with matrix multiplication. Of course, it would be very convenient it would be very inconvenient if we, for translation, have to do it always. If we can do everything with matrix multiplication, and matrix multiplication is supported by hardware, though we can also do it very fast. But just for this one single thing, we need to do something else. that would be very inconvenient and would make our code much more complicated. It's not hardware supported. So of course, we really want to do it with matrix multiplication. So the solution is people came up with a way to do it, which are these so-called affine transformation, which is an extension of the linear transformation. So affine transformation are basically a combination of linear transformations and translations. Be careful with that. That's a common mistake in multiple choice questions, that people say affine transformations are just translations. That's not the correct definition. The correct definition is affine transformations are linear transformations and translation. Yeah, and yeah, let's make a little break here, and then I tell you how this works after the break.